Welcome to Deep Learning. So in this little video, we want to go ahead and look into some basic functions of neural networks, and in particular, we want to look into the softmax function and look into some ideas how we could potentially train the deep networks.
We have a search technique which is just local search, gradient descent, to try to find a program that is running on these recurrent networks such that it can solve some interesting problems such as speech recognition or machine translation and something like that.
Okay, so let's start. Activation functions for classifications. Now, so far, we have described the ground truth by labels -1, +1, but of course we could also have classes 0, 1. Yeah? So this is really only a thing of definition if we only do a decision between two classes. But if you want to go into more complex cases, you want to be able to classify multiple classes. So in this case, you probably want to have an output vector.
That does not show any pictures.
And here you have essentially one dimension per class K. So K, capital K here is the number of classes. And you can then define a ground truth representation as a vector that has all zeros except for one position, and that is the true class. So this is also called one-hot encoding, because all of the other parts of the vector are 0 and only a single one has a 1.
Of the world in vector space. But I think this is very difficult for normal people to understand. They would not know what the heck they're looking at.
And now you try to compute a classifier that will produce a respective vector. And with this vector y hat, you can then go ahead and do the classification. So it's essentially like guessing a output probability for each of the classes. In particular for multi-class problems, this has been shown to be a more efficient way of computing these problems. Now the problem is you want to have a kind of probabilistic output towards 0 and 1, but we typically have some arbitrary input vector x that could be arbitrarily scaled. So in order to produce now our predictions, we employ a trick, and the trick is that we use the exponential function. So this is very nice because the exponential function will map everything into a positive space. And now you want to make sure that the maximum that can be achieved is exactly 1. So you do that for all of your classes. So you compute the sum over all of the exponentials of all input vectors or of all input elements, use the exponential function on them, sum them up, and this gives you the maximum that can be attained by this conversion, and you divide by this number for all of your given inputs, and this will always scale to a 0, 1 domain, and it will have the property that if you sum up all elements of the vector, it will equal to 1. This is very nice because these are two axioms of the probability distribution introduced by Kolmogorov. So this allows us to treat the output of the network always as kind of probabilities.
And that was my 1987 diploma thesis, which was all about that.
And if you look in literature or also in software examples, sometimes the softmax function is also known as the normalized exponential function. So it's the same thing. Now let's look at an example. So let's say this is our input to our neural network. So you see this small image on the left. Now you introduce labels for this 3-class problem. Wait, there's something missing.
Open your eyes!
Yeah, it's a 4-class problem. So you introduce labels for this 4-class problem, and then you have some arbitrary input that is shown here in the column xk. So they are scaled from -3.44 to 3.91. This is not so great, so let's use the exponential function. Now everything is mapped into positive numbers, and there's quite a difference now between the numbers. So we need to rescale them, and you can see, tada, the highest probability is of course returned for heavy metal in this image.
And the darkness withdraws!
So let's go ahead and also talk a bit about loss functions. So the loss function is a kind of function that tells you how good the prediction of a network is. And a very typical one is the so-called cross-entropy loss. And it's the cross-entropy that is computed between two probability distributions. So you have your ground truth distribution and the one that you're estimating, and then you can compute the cross-entropy in order to determine how well they are connected, how well they align with each other. And then you can also use this into a loss function. Here we can use the property that all of our elements will be 0 except for the true class. So we only have to determine the negative logarithm of y hat k, where k is the true class. This simplifies the computation a lot, and we get rid of above sum. By the way, this has a couple of more interesting interpretations, and we will talk about them in one of the next videos. Now, if you do this, we can plug in the two and construct the so-called Softmax laws. And the Softmax laws, you can see we have the Softmax function in there, and then we take the minus logarithm here only of the element that has the true class. And this is something that is very typically used in training of networks. So this softmax loss is very commonly used. Very useful for one-hot encoded, and also very nice, it kind of represents a histogram. So it's very much related to statistics and distributions. Also, all of the multi-class problems can be handled in this approach in a single one go. The other thing that I want to talk about in this video is the optimization. So one big thing that we haven't considered at all is how we actually train those networks. And we already seen that there are these hidden layers that cannot be directly observed, and this kind of brings us in a very difficult situation. And you may argue that the image here on the right is very similar to the one on the left. If you change anything in this chain of events, it may essentially destroy the entire system. So you have to be very careful in adjusting anything on the path, because you have to take into account all the other processing steps. So this is really hard, and you have to be careful what to adjust in what way. Now we'll go to the easy way, and we'll formulate this as an optimization problem. So we already discussed that we need some kind of loss function. The loss function tells us how good the fit of the predictions is to our actual training data. So the input are the weights, w, then x, the input vector, and y, which is our ground truth labels. And we have to consider all m training samples, and this allows us to then describe some kind of loss. So if we do this expected value, which is essentially a sum over all of the observations, and this sum, scaled sum, then is used to determine the fit to entire training data set. So now if we want to create an optimal set of weights, what we do is we choose to minimize this loss function with respect to w over the entire training data set. Well, now we have some mathematical principle that tells us what to do, and we know minimization. Let's try one of the obvious choices, and the obvious choice is gradient descent.
The stuff that works best is really simple.
So we choose to find the minimal w that minimizes the loss over all training samples. And in order to do so, we compute the gradient, and we need some initial guess for w. There's many different ways of initializing w. Some people are just using randomly initialized weights, and then you go ahead and do gradient descent. So you follow the negative gradient direction step by step until you achieve some certain minimum. So here you can see this is initialize w in step 1, maybe randomly. Then step 2, iterate until convergence. So you compute the gradient with respect to w of the loss function. Then you need some learning rate eta, and eta essentially tells you how long the steps of these individual arrows here are. And then you follow this direction until you achieve a minimum. Now eta is commonly referred to as the learning rate. The interesting thing about this approach is it's very simple and you will find some minimum. It may be only a local one, but you will be able to minimize the function, and what quite a few people do is they run several random initializations, and those random initializations are then used to find probably different local minima, and then they simply take the best local minima for their final system.
And there is very little theory behind the best solutions that we have at the moment.
What is this L that we're trying to optimize? Well, L is computed here at the very output layer. So we put in the input into our network, process with the entire network, and then in the end we compute essentially the difference or the fit or the loss to our desired output. So you could say if this is the first layer is F, the second layer is G, then we are interested in computing L as some input X and W, compute F, then use the weights W and G, compute G, and then in the end we compute the fit between G and Y. So this is essentially what we need to compute in the loss function. You will see that this is slightly more difficult. So we will see that we need to be able to do this efficiently, and there's a very efficient algorithm to solve such kind of problems, and it's called the backpropagation algorithm, which will be the topic of our next lecture. So thank you very much for listening, and see you in the next video. Thank you.